Now we talk about geometric factors. Geometric factors have everything to do with lines and planes and angulations. So when we're referring to geometric factors, now we're getting into actual sharpness, recorded detail, and the size and length and sharpness of the image that we're trying to record. So what controls our geometric factors would be anything that distorts the image or blurs the image. So I have magnification, distortion, focal spot, anode heel effect. Those all affect our spatial resolution, and that is the ability to differentiate adjacent lines, and it's measured in line pairs per millimeter. We talked about that in class on Tuesday. Things that affect sharpness of recorded detail would be motion. Motion is the one thing that you are not completely under control of. You can limit the likelihood that you'll see motion on the image receptor or on the image by giving the patient good instructions and also by using the shortest time possible, or shortest time feasible anyway. So focal spot size, the focal spot size is what you use to control sharpness of recorded detail. Positioning, though, you can also use. And in positioning, you want to utilize the lowest OID and the longest practical SID. But we also have some image receptor issues that we talked about in the last recording. So backing up to here, magnification, we control magnification with SID and OID. Distortion, we control by maintaining a perpendicular relationship between the part and the X-ray beam, and also a parallel relationship between the part and the image receptor. Focal spot, we can use large and small. Large is whenever we want to expose a large anatomy with a large exposure, so high mass value, and small whenever we want to see fine detail. And anode heel effect, we'll talk about where we see it better, where we see it worse, where we can utilize anode heel effect to try to get a better overall contrast, density, and sharpness for recorded detail. We tend to focus on contrast and or not really contrast, but density differences between one end of the X-ray tube and the other, but there are some geometric factors to consider there as well. So magnification all by itself is nothing but size distortion. And you need to understand magnification is always present. The magnification is controlled by SID and OID. And OID is really the portion of that equation that makes magnification always present. You can never achieve a zero OID. Even on thin anatomy like your hands, you're going to have an increase in OID because of the soft tissue. The soft tissue prevents you from putting the bones directly on the image receptor. Even if you could take the bones and put them directly on the image receptor, you're still going to have a distance between the thickest portion of the bone and the image receptor. So you're still going to have an increase in OID. So if you remember your magnification factors and your calculation of magnification factors, you've got two different things. You got magnification factor, which is always a image size compared to the object size, and it's always a measure of 1 point something. So 1 would represent a magnification factor, or 1 would represent that there is no magnification present. You always have a magnification factor of 1 point something. Now, when you're talking about percentage of magnification, that's something totally different. But whenever we're talking about magnification factor itself, then we're talking about your magnification factor always being 1 point something. It's always greater than 1. So magnification occurs by changing SID and OID. If you increase your OID, it's kind of like increasing your the shadow size whenever you raise your hand off of the table if you're looking, or your desk, or whatever it is that you're looking at. If you elevate your hand towards a light source, then you get a larger shadow. And the same thing holds true in X-ray. So if you increase your OID, you increase magnification. What we use to overcome that magnification to a degree is an increase in SID. So if you keep your ratio of OID to SID the same, then you can negate the effects of an increase in OID. What I mean by that is if you increase your OID by a factor of 2 and you increase your SID by a factor of 2, then you can overcome the increase in magnification because of the increase in OID. So magnification is always present, especially with spherical shaped objects, because you simply cannot get the thickest part of the anatomy closest to the image receptor. If you had a round ball, the only way that you could overcome magnification, the only way you would not have an increase in OID, is to cut the ball straight through the thickest portion of the ball and put one half of those spheres, the flat side, down on the image receptor. That's the only way that you could possibly overcome magnification or not have magnification present with a round object. So with magnification comes loss of sharpness or recorded detail. So back to this slide, with magnification factor calculated as image size over object size, then the image size, again, is always going to be larger than the object size. So if you divide the image size by the object size, with the image size being larger than the object size, numerator divided by denominator, you're always going to come out with 1 point something. That point something would be your percentage of magnification. So if your image size was 1.1, or let's say 11 inches, and your object size was 10 inches, then your magnification factor would be 1.1. So in that 1.1, what you have is the image size is 110% larger than the object size. So that 1.1 is really a percentage. So your image size is 110% of your object size, which means that you've got 10% magnification. I'd refer you back to your math quiz lectures, the lectures over the first 2 math quizzes, and have you review calculation of magnification factor for the test. So image size is always greater than 1. Image size is always greater than 100% of the object size. So actual image size is dependent in a digital world on collimation and other factors. So when we're talking about the image size, what we're talking about is the actual shadow that would be on the image receptor. The display image size is going to be dependent on a lot of different things, including the size of your collimated field. We talked about that in class on Tuesday as well. If you don't collimate, then the computer is using the overall exposed area to determine how large of an image to display to you. So if you don't collimate for a finger and you use a 11 by 14 size field for a finger, then it's going to give you an image based on that collimated field and not the anatomy itself. So the display on your image receptor is going to make the finger look like it's very, very small. So it's going to look like you've got a decrease in magnification. And that's not really what we're talking about with these formulas up here. With these formulas up here, what we're talking about is the actual shadow on the image receptor that would go into the creation of the image and make it look true to size. So source to image distance, SID, you know what that is. Most commonly we use 40 and 72 inches. Some of your textbooks use 48 inches. So changes in SID without any other changes do a lot of different things. They change the exposure to the image receptor. It's what we used to call density. So it's going to affect your S number or your index number. So if you increase, according to the inverse square law, if you increase your SID, then the intensity at the image receptor is going to decrease. If you change nothing else, then the intensity is going to decrease. If you do increase, then obviously you need to increase your mass. It's also going to affect your sharpness of recorded detail. The further out we are, the further our SID, the better the sharpness we're going to see. And again, that's part of the reason we use 72 inches in some cases when we have an increase in OID. The increase in SID brings that magnification back down, but at the same time, it reintroduces sharpness of recorded detail. And we have a reduction in magnification with increased SID, but it really has no effect on contrast. Changes in SID don't affect the PE ratio inside of the patient. They don't really affect the scatter radiation unless you have a drastic increase in OID that accompanies the SID. But the SID change all by itself should have no effect on contrast. Again, full disclosure, whenever you have a significant change in density, and you were to look at the raw image and compare the raw image, you might get the appearance of a change in contrast because you're going to have such a different change in density. So the overall image appears lighter, and to your eyes, in a lot of cases, it looks like a change in contrast, but it's really not. So contrast, again, is controlling the PE ratio, which is controlled by, that's the Compton to PE ratio, and what strikes the image receptor, and that's really caused by changes in KVP and grid use, and also tissue type. So increased SID, decreased magnification, that would be like the difference between an AP thumb versus PA thumb. You change your magnification. So object image distance, you also know what that is. That is your OID. So with changes in OID, you get a change in density, and it's not because of the inverse square law, it's because of the air gap technique. So you increase your OID, and especially in tissues where you cast a lot of scatter radiation, that scatter radiation might be projected off of the image receptor, so it completely misses the image receptor, and it reduces the exposure in the anatomy of interest. So whenever we increase OID, we should increase technique. If you phototiming, really you don't have to do anything, but if you increase your OID on a set technique, you should increase your mass. Because some of that scatter radiation misses the image receptor, then our contrast should improve. Textbook says it works kind of like a low ratio grid, and if it does work like a low ratio grid, it's only going to be about a 2-to-1 or 3-to-1 grid. It's pretty insignificant, the amount of density and contrast that changes with an air gap technique. But it kind of makes it sound like you could use no grid on lateral C-spine because of the increase in OID, the air gap. And I can tell you can see a significant difference on film anyway if you use a grid versus not using a grid. So some of the scatter probably misses the image receptor, definitely misses the image receptor, but as far as scatter cleanup and improvement of contrast, is pretty minimal. It does affect your sharpness of recorded detail. If you increase your OID, again, you're back to elevating your hand with off of your desk and towards a light source. What you should see is a much fuzzier image. I kind of demonstrated that in class on Tuesday. If you increase that distance, that OID, you're going to lose sharpness of recorded detail. Magnification is going to be present, and magnification is size distortion. It's an overall increase in the size of the image. So how we overcome that is with an increase in SID. If you double your OID and you double your SID, then your magnification remains the same. So SID and OID, just a graphic demonstration of that. You know what those are. SOD is source to object distance. So SOD is always going to change whenever you change your SID, your OID, or both. So it can affect magnification and penumbra. Remember, your penumbra is your unsharpness, and umbra is your sharpness. So penumbra being unsharpness, that is the fuzziness whenever you increase your OID. Mathematically, this is where people kind of get lost in calculation of magnification factor. Remember, SOD, source to object distance, is SID minus OID. So what the thing that people tend to skip is whenever they're calculating magnification factor is that they seem to skip over SOD. So in a lot of cases they'll go SID over OID. Well, no, it's SID over SID minus OID. So how do we control magnification factor? We use the lowest OID possible. But anything that we put in between the actual image receptor and the patient increases OID. So whenever you're using a grid or you've got the image receptor inside the bucky, you're naturally going to have an increase in OID. So every KUB you shoot, as long as you're using a grid, further increases OID. We've already mentioned that you're always an increase in OID is always going to be present because of the thickness of the anatomy. But anytime that you use a grid or a bucky or both, then you're going to further increase OID, which is going to increase magnification. So you just need to be aware of that. And then we're going to utilize the longest SID practical. So 72 inches for a KUB is not practical. In order to achieve a 72-inch SID for a KUB, a supine KUB, what you would have to do is put the patient on the floor. There's nobody in our class that would be able to reach up 7 feet. And as a matter of fact, our towers won't telescope up to 7 feet from the image receptor with the image receptor into the table. So it's important to understand longest SID practical. You can't get the longest possible SID on every image. So back to where we were discussing the most common SIDs, 40 inches and 72 inches have been the benchmark for my entire career. I don't remember if it was the last edition of Merrill's or the one before, but they tried to kind of change the 40-inch SID to 48 and try to get that to be the established norm, but it just never really took off all that much. So they leave that in the textbook in some cases as maybe a passive-aggressive way to try to get people to increase their SID, but it's just not taking off. Now, when we're talking about changes in OID and SID, it's important to understand that there are times that we want intentional magnification, and those exams are what we call macro radiography. We don't see it a whole lot anymore. With digital processing, we can magnify the image without having to use an increase in OID. But if you read a question that refers to macro radiography, that is intentional magnification. So again, if you double your OID and you double your SID, you don't increase your magnification. So with macro radiography, what you have is an increase in OID without an increase in SID. This is not the same thing as an air gap technique. You're probably still going to use a grid with macro radiography, and it's probably going to be a fluoro case where you're using a C-arm, and the intention is to magnify up to small blood vessels. But since we're using such an increase in OID, which is going to give us the magnification, what we need to do is not increase SID because we want the magnification present, but with the increase in OID, we get a loss of sharpness recorded detail. So what we're going to use is what we call a micro focus X-ray tube, which is a very, very small filament with a very steep anode bevel angle. And in most cases, again, we're going to use these in interventional where we're looking at very small blood vessels that without magnification are too difficult to visualize. So we're looking for small defects, presence of bulges that will eventually become aneurysms, things like that, any kind of filling defect inside of a blood vessel. So we'll want the magnification, so we'll want to increase OID, but we don't want to increase SID. If we increase SID, then the magnification decreases again. Macroradiography is intentional magnification, presence of OID, increase in OID, without the increase in SID so that we can see those things. We overcome the loss of sharpness or recorded detail by using a small filament, very small filament with a steep anode bevel, which gives us what we call a micro focus tube. So the heat load on these things are going to be pretty massive, and how we overcome that is with larger anodes, in a lot of cases that rotate very, very fast. So in interventional, your rotating anode the speed of your rotating anode may be as much as 10,000 RPM as opposed to 3,500 RPM in diagnostic.